Hi, Rémy.
Hi, Adam.
So today we wanted to chat with everyone about versioning in TuringDB and how we came to create it and the story behind why we created versioning and how we created versioning. So maybe we can share a bit those ideas behind it.
Yeah, yeah. So versioning is basically one of these new things that we introduced in TuringDB, and I would like to say introduced into the world of graph databases in general, because to our knowledge, it has not been done before in this form, right? Um, First, maybe what we mean by versioning. So what we mean by versioning is Git-like versioning. Basically, TuringDB is a graph database, right? And so you can create nodes and edges in your graph successively. So you can add node, add edges, add node, add edges as you wish. And what we do is that every time you add a new bunch of nodes and edges, for us in TuringDB, this is a commit. This is a commit like in Git. So this is a commit, if you wish, a snapshot of the database. Maybe there is one first commit when we import the graph from maybe a CSV file of nodes and edges, or by doing a bunch of initial create commands in Cypher. But that constitutes the first commit, like the initial commit of a Git repository, right? And then if we issue modifications or add new nodes and edges against it, this will be subsequent commit on that main branch of the graph, just like in Git, if that makes sense.
Yeah, yeah,
And and basically the point is, okay, we have different commits, and the idea is when we query the database, basically any query is run against a particular commit, so against the latest commit in existence in the main branch when your query comes in, right? Or you can actually specify a particular commit of the past, just like in Git when we do Git checkout to basically check out at a particular version of the past, because maybe you want to go back into any previous state of your database, but basically you have a well-identified point, which is a commit, which is a snapshot again, against which your query will be run. So it's not like in classical relational databases of, yes, you have obviously a concept of transactions, where a transaction is basically I'm seeing a somewhat isolated, or not actually, a somewhat isolated view of the data. And when I'm reading the database, I'm not seeing basically things that are partially being written by some concurrent user and so on and so forth. And so I am kind of in my own little private view of the database. But basically, in traditional database systems, this is kind of implicit. These transactions are implicit. The users cannot name them, right? A user in MySQL, PostgreSQL cannot name a transaction and say, I please execute my query against past transaction, blah, blah, blah. It's you are given your own private view of reality, but you cannot go and execute your query in the past. And so what we do with TuringDB is that every transaction ever done, every write transaction that ever modified the graph still exists as a commit of the database. So we have a history of commit, and it works exactly like in Git. I can say, please execute my query against the, let's say, the latest and the tip of my main branch, basically the latest commit, or I can query my database against any point in the past, basically, against any possible modification that was ever done to my graph, basically. Um, and that's just over one branch, right? Because Git, if you know, you have this crazy system of branches. I mean, practical to some, but crazy to understand in some cases. But that's okay. In our case, it's fairly simple. I will just stop there before speaking about branches. I don't know, Adam, if that makes sense from your end.
yeah. I think you covered it very well. Generally speaking, I think I would come from maybe an application side before to go into the branches and those details, because that's always what I like to look at too. Um, Basically, I think to rewind a bit historically why we implemented versioning, could you also a bit like deep dive in those concepts we share about why building graphs, um, being able to go back in the past to this graph is important. So, for example, in healthcare, we wanted to have multiple models of the same graph that we are able to compare and see when we can merge back or go back in time. So we can have those different graph models, let's say, and at the same time ensure auditability, compliance, governance, because you make sure that your graphs are managed by the right people at the right place at the right time, and you can go back in time because if FDA asks for something, you need to better go
Yeah.
go back to it, and it's never been changed. It's immutable. So if you can go in those two concepts, would be great because I think from an application point that explains why it exists too.
Yeah. So absolutely, as you said, from in any industry where basically you have regulatory constraints, we call them sometimes critical industries, but like industry like healthcare, life science, when I'm basically making drugs for health, when basically I'm maybe working in an insurance or in a banking context, or all these industries where we have basically huge regulatory requirements for good reason. Um, Once a change is made, so like if I'm a pharma company, maybe I have a gigantic knowledge graph of everything relative to my drug, all the biological mechanisms happening in patients for my drug. For example, if I am a big pharma company in the business of making drugs for liver cancer, for example, I will have maybe a gigantic knowledge graph of everything happening in the liver, kind of mind map for scientists of what's going on in the liver. Actually, I think that would be a pretty good idea. At least, I mean, we are graph database people, so obviously we won't say this is not a good idea, right? Anyway, let's say you have your knowledge graph of what's going on in the liver, and out of the knowledge encoded in this knowledge graph, you are basically making your new awesome liver cancer drugs. So basically, like when you will go to approval for your drug in front of regulators, rightfully so, maybe the regulators will want to see the data. Okay, so basically they will want to see the data in the sense of the statistical data, like the numerical statistical data of the clinical trial stages, what has been tested on animal models perhaps, or in the lab, and so on and so forth. But also the knowledge you have encoded in the graph and the conclusions you have derived from this data encoded into the graph. And so the graph becomes basically on what you based your design of the drug, on what you base it's your justification basically to build your all your regulatory papers that you've write as a pharma company in order to go to regulation and potentially go to market to your drug. So there is an enormous amount of basically millions of dollars, right, with your drug project as a pharma company that stands on the quality of the evidence and the quality of the data and the insights that you have generated all along the journey of your drug. So this is why uh, basically, as a pharma company, you need, let's say, a lot of rigor and seriousness with the way you manage your data. And so once a set of insights or a set of conclusions on your data has been recorded, it must be kind of recorded forever and in a canonical form. So it cannot be changed or it cannot be touched by mistake by somebody in the team. So this is why it's really important, I think, and very helpful to have that notion of commit, such as, because like in Git, if you don't know, once you create a commit cannot be changed. So yes, there is a git commit amend option for those who know. It's true, but in fact, it's fake. It still internally creates, in fact, a new commit that contains the modifications that you want on your existing commit. So it's always a different commit once a commit is done in a Git-like system, it's done forever. It's immutable, how we call it. So it's immutable because it means that it cannot change. Once a data is committed, it's really there. And so I can really go to the regulators and show it as a body of evidence to, okay, I have good data tracking perspective, I have good data governance practices, basically, that ensures that my data has been modified and basically written at well-defined time points. I don't have somebody an intern that came in and bamboozled everything, or may have corrupted basically the quality of the evidence that I'm submitting. And so outside the pharma sector, we may understand that, for example, a lot of financial industries obviously are basically subject to financial regulation and different audit requirements. So it's also like, especially if you want to submit, I think, to a regulator or to some kind of institution performing an auditing on you as a financial institution, if you want to show, for example, what are your fraud detection and prevention practices, it could be very interesting to say, okay, these are the sets of graphs on which we have performed this and this analysis. These are the type of fraud patterns we have seen that we are actually able to detect. So people can even perhaps take your algorithms in some ideal scenario. If we really want to do auditing in the sense of even do reproducibility, we can even take the graph data as input, take the algorithm and say, okay, indeed, we can detect these fraud patterns on this given input. So this is why reproducibility, whenever we are in well-regulated and strongly regulated industries, this is really, really important. And also, besides regulation, I think the practice of using Git and the popularity of Git and GitHub for developers now have shown that it's a great way to do collaboration, because otherwise, like if you have a team of data scientists, what are the options to collaborate on a given data set, in our case, on a given shared graph, a given shared knowledge graph in a company? Like, frankly, what are the options? One options would be, okay, if you use Neo4j, you use Neo4j on your machine or Neo4j desktop, it's a huge, gigantic folder on your computer or on a computer somewhere, but then how do you share, right? So, and then if it's Neo4j server or Neo4j Aura, then anybody can write, anybody with the authorization on the graph can write. And so if you have, for example, let's say you have an intern, there is a classical intern problem where you may have an intern coming in. They may think they are doing a bunch of very clever modification on your knowledge graph. And then you come back on Monday and then, guess what? Half the company knowledge graph has disappeared. What surprise? Or actually, it's not really the intern fault per se. It's perhaps you have a data pipeline which is quite buggy, and it's in fact the action of a script that actually, by mistake, deleted or added a bunch of things in your graph by mistake, or because the algorithm was not quite correct. It can happen. So anyway, all that to say is that in this type of circumstances, when you collaborate, as soon as you collaborate with multiple people or multiple pipelines and you have a lot of things going on, it's a good idea to not touch your company single source of truth, immediately. It's a good idea to maybe allow the intern to proceed with their project in a separate branch of the data, so in a separate branch of the graph for us. And then during the week, you will have time with the team to actually review the changes of the intern and possibly decide to merge the intern project into what's the main branch, into the main single source of truth of the company if you are happy with those changes.
Totally. I agree. I think it also came from personal experiences that we ended up building it because we experienced both the intern and the need
Yeah.
of going back to previous versions. Yeah, I think it makes sense. So I guess maybe we can go into the what you were mentioning about the branches and merging and a bit those underlying concept. And I guess also you have a whiteboard behind, so you can also feel free to use and be creative with it.
Yeah.
But yeah, so basically would be interested to explain a bit how we implemented that, I guess, from a technical point.
Yeah. So I will just try to do a drawing of this thing about commits, right? I hope you
Yeah,
can see the drawing board.
so far, yeah.
So far, yes. Okay. So let's see. Um, so conceptually, basically you arrive and your graph is initially empty, right? I
Yeah.
don't know if you can see
Maybe
that.
push it a bit back and we'll see.
Okay.
Yeah, I think it's better. Perfect.
Okay. Um, and so your graph is empty. And so let's say initially you will add some nodes into the graph to start with. Here I have just
Yeah,
3 nodes and a couple of edges. And basically it will be the initial commit of the database. Okay, so it's exactly when in Git we do initial commit with our first code. Here it's the initial commit with the first nodes and edges. Okay, and so my history of the database can build up like this. I basically, if I add a new node because I want to do modifications, so actually I'm maybe adding more data and performing more create queries like this, I will have a subsequent commit after the initial one. So it will be like commit number 2, and this is commit number 1. And so in that commit, I will have my new node in blue and the 2 edges going out of it. And so basically, this is the commit history of my database. And so each time I do modifications or I add nodes and edges or I perform deletions, this will create a new commit on top in my history. And so, for example, if I have a query now coming in, for example, if in Cypher I arrive with a query doing match and return n, I'm just writing the most stupid query ever in Cypher to say, okay, return me all the nodes, just because I have not so much space in the whiteboard. But basically, this query will be executed against the latest committed data in the database. So basically, the latest commit is now this one. Okay, and so this query match n return n will return, actually, if I give names to nodes A, B, C, and D, when I am at this commit 2 in Git, I see the first nodes A, B, C that I added in the initial commit plus node D. So what I will return will be this column containing A, B, C, and D. And we can see that indeed, when I am at this commit, if you wish, that view of reality is that one. So I can also choose to basically check out a particular commit, meaning to execute this query at a particular commit in the past at an arbitrary point in the past, because every modification ever done to my database is recorded as its own commit. So we can go arbitrarily far into the past and do like a kind of time traveling. This is very fun. Um, if you can sleep at night, for example, or no, I'm joking. This is really useful to actually, see what has been changed. And so basically, I can explicitly say, please run my query now, only again the initial commit to see what's different. And in fact, indeed, what I will get obviously here is only nodes ABC in red, which were the nodes present initially in my first insertion. So yeah, I can go back arbitrarily in the past. I can do time traveling. And this is a single branch, okay? Because we see that's just commits that are nicely put one after the other. And I would say one on top of the other in a sense, because when you are here at commit 2, you have node D on top of ABC. Okay, so obviously our graph database engine, when it executes a query, has to somewhat transcend all the data that was inserted in each of these commits and have a view of, okay, it's like when you have these transparent sheets in, I think it's a thing for the people of our generation in high school when, teachers were doing drawings on transparent sheets when you didn't have video projection yet. Come on in, at least money-deprived public schools. So, you see all the data by transparency in a way, so you have to go to each of these commits. And we have some magic to do it. Anyway, yeah, so this is just one branch. But as I said, there is the well-known intern problem, which is when we collaborate with multiple people or actually also non-human entities, such as pipelines and scripts, we may want them to perform what they have to do in their own isolated view of the database. And more than just a view, we want them to operate in their own separate branch. So what happens is that we can totally create a branch out of any commit. So here, okay, I could totally execute a script that would modify arbitrarily my graph just up here in the main branch, creating a commit free, and modify the database in a way that would be visible for any query that comes afterwards. If I'm really bored or if I'm sure, yes, absolutely I can. But actually, maybe this is a good idea to do my change in my own private branch. So we have this command called change new currently, where we can basically branch off commit 2, for example, here, and create some commit 3 here. And so here I'm in my own private branch. So as you see, this is not connected to the main history of my database. So if I have a new query coming in, basically, if I have a new query match n return n coming into my server, it will still be executed against that commit, which is still the top of the main branch, which is still the latest that I can get on my database in the main branch. Okay, so here I can do whatever modification I want in my parallel branch. It will not be visible by anybody else. And so actually I can continue and create a bunch of other commits if I'm working in my parallel branch. And here it won't be seen by anybody else. So I'm totally isolated. I have no possibility of interference with anybody else, okay? Because all the other queries will be coming in on the main branch, or at least in their own private branch. And what this also means by branching is that obviously we can continue to have activity on the main branch, meaning the intern can continue to add more data and work on their own project, on their own private branch. That's fine. We can we can actually continue to add data that we are very sure of in the main branch like this, okay? So now it looks like really like a private diverging history of sorts where we have somebody doing their own thing on the side. That's okay. And then we have everybody else that sees the true, the standard of truth, basically, that is working on the main branch. Um, but if we see divergence, right, there is a point of how do we combine? How do we merge back? How do we maybe integrate this work, which is actually maybe very, very valuable? And now I want to integrate my change into the main branch back and to add it on top. And that's exactly what software developers do now with Git and GitHub or GitLab. They may be working on their own new feature of my app, on their own private branch with their own private push requests. And then the senior developers come in and they say, please do these and these changes because this is not quite right. And when everybody agrees, basically, this is good to go. And you know that private new features that they developed on the side has to come into the main state of the app, if you wish, into the main code of the app, if you wish. It has to be integrated into the main branch of the app. And so in any Git-like system, we want to merge this private branch at some point into the main branch. And so we implemented an automated merge feature, which is basically whenever you type change submit in TuringDB and you are in your private branch, this will be basically merged into that one. So how does the merge work, right? So what do we want? Conceptually, first, we want to somewhat put everything which has been done here in the private branch into that one. Okay, we want to do we want to put it on top. That's, if you know about Git, that's what's called a rebase, and that's exactly what we want. As we know, a rebase is quite complicated. Anyway, I will just explain intuitively for everybody. So you have your private changes. Maybe they added a bunch of nodes and edges on the side, whatever. Maybe they linked existing stuff. Okay. And what TuringDB does, again, automatically for you, what we do is that we do basically surgery. So we take these two guys that were in the parallel branch and we put them on top of main. Hurrah. All right, so I will redo my little drawings I had before, just so that we are sure. Maybe we don't really see anymore. That's okay.
Okay.
So yeah, basically I've put everything that was in the private branch into that one. So putting on top, I won't go into it, but just a little bit of disclaimer. This is not so trivial as it sounds. It's not in general just basically connecting the commits, connecting the references, and everybody's happy. Obviously, otherwise it won't be fun. We understand, for example, what if the intern changed, for example, the age of somebody or an intern, let's say in a pharma company, you have a graph of patients and the intern changed the age of a patient suddenly to 55 instead of 42. So what happens? You have a conflict, right? You have on one side a patient that was 42 and now it must be 55. What do we do? What do we keep? Okay, is it the branch and the contributions incoming from the interns that wins, or is it the 55? Hard to say. So if you are merging something onto main, it's the new age that takes precedence, basically, that is put on top. But What if you had concurrent changes? What if the intern changed the age to 55 and somebody else was like, actually, I've asked the person. That's a good idea to ask the person in person, and to say, actually, their true age is 64. So now your intern has decided that this poor person is 55, and that person says that they are in fact 64. So we have kind of two conflicting informations on each side. Well, we can say, at least TuringDB cannot say. TuringDB wouldn't phone that person to know, right? So what can we do? What can we do? The answer is basically conflict. We have a duty to actually give to you, the user, there is a conflict. These two contributions, these two changes to the database cannot be merged as they are. So it's up to you. You have to actually decide and reconcile them. Is the intern actually right? And the patient may have lied, or is it actually the patient that is the best to know their own age, perhaps. So, that's the notion of having a conflict. And so sometimes automatic merging in databases in general is not so simple. And so now that I think that brings us to the topic of isolation and conflicts and all this nasty business, right, Adam?
Yeah, yeah, indeed. I think it's I mean, from an engineering point, it's something that's not, as you say, straightforward to implement. Um, and uh, and I think from a data governance point and auditability, the aspect of full snapshot isolation that comes with it. Also the concurrency you mentioned is going to be an interesting topic to cover at some point. But yeah, so maybe at this stage we can do a short conclusion on the the versioning system. You can mention quickly those aspects of isolation for specific commits, how to run them, query them, and then next episode we can cover some of those a bit more in detail.
Absolutely. So basically, in terms of how can I query the past, yeah, how can I go in practice in TuringDB to any previous commit? So that's easy if you directly use TuringDB locally using the TuringDB CLI. It's easy. We do have the checkout command where you can say checkout commit one, commit two, commit three to go back to any commit that you wish and execute your queries against that commit. If you use TuringDB in a server mode, and so therefore you use our Python SDK, again, we also have a checkout function in Python. It's very easy. You can just say checkout the commit I'm interested in. So in terms of isolation, that commit system, we have to understand this is what basically provides us an extremely strong, I would say, sense of snapshot isolation. So, in databases, you have different ways of being isolated of the work happening in parallel in the database or the modifications that may be done by other people in parallel on the database. And kind of the strongest we can practically have while still allowing things to proceed in parallel is what is called snapshot isolation, which is that you give to every user coming in on the database their own private view of reality, their own private view of the database, whether they are looking or making changes. So basically, so you don't want obviously to completely duplicate the database for every user, but you want everybody to come into parallel against the same server, right? So we can give that trick and that illusion of being in your own private view of the graph by using this versioning system, because as I said, once a commit is done, it's done, right? The commit cannot ever be changed. So if anybody is doing preparing a subsequent commit on the same branch, that's okay. You are just in the past, right? Nobody can ever touch your commit, so you are fully isolated. Nobody can change the data you're reading. You cannot see the writes to the database that are being built. And obviously, if the writes are happening on a completely different branch, that's even better because you can't see it at all, right? So to conclude, basically, versioning, we thought it first, I think, for collaboration, for a way to do auditability better, to do team collaboration better instead of whatever has been done, over the last 40 years in databases and say, okay, nothing to see here, let's go home, No, we can actually collaborate better, as we mentioned. And then we saw that it's actually a very good way to provide full snapshot isolation level, which is something that is nearly never done for graph databases, really, because everybody may say, it's snapshot isolation, except in these cases, please don't look too much at it, kind of embarrassing. I won't give names, but the usual suspects usually. But yeah, once you have a Git-like system, you have your commits. Once it works, it gives you basically full snapshot isolation kind of for free, basically.
Yeah, it's brilliant. Yeah, I think it's something that also touched for us a lot on aspect of reproducibility in life science. There's in science in general, there's a crisis of reproducibility. And I guess it's starting to also crawl a bit everywhere now with AI models kind of, dumping stuff, etc. So you want to make sure you always have your source of truth clean and you can go back in time. So makes a lot of sense. I think at least for us when we created it for us first and then
Yeah.
now giving it to the world, let's say. So yeah, I think we kind of covered all the big points of versioning within TuringDB from a high level. If people have specific things they want to dig in, don't hesitate to let us know. We are always happy to share more info and share Remy's wisdom on those things. So yeah, thanks to anyone that watched all the way here, and and a little hello to you, and yeah, thank you.